Yeah, thank you very much, Alex, and thanks to the organizers, Sarah, Scott, Robizon, for putting together this really fabulous conference. And thanks, Thomas, for the first talk. So this is a joint work with Marcus Brunemeyer, who's one of my former teachers, and some of you may know him. He's a finance professor at Princeton, and also Carlos. Carlos is at the Central Bank of Costa Rica. I met him when I was visiting UPenn. He was a PhD student there, and he wanted to go back home, so he's back in Costa Rica. So what we want to do here is kind of take the classical question of kind of insurance markets, almost a textbook model that we teach students in graduate class about how to think about insurance markets. The starting point is really that maybe the classical way in which we think about some of these models is that you walk into an insurance company and you have some private information about the probability or the extent of damage that you may incur from an accident needs to be kind of updated. And so there's a lot of discussion right now in popular media, in journals, in academic work as well, saying that, that insurance companies actually may know some information that you may not know about the probability of getting sick or probability of getting into an accident and so on. Okay, and there was a very interesting, last summer, there was a very interesting kind of series of articles that New York Times did that is very relevant to the topic of this conference that I highly recommend people look at. It's called The Privacy Project, in which they discuss some of these issues. Here is another example from a headline where Google has been able to now store health information on millions of people, and now can it monetize this? So broadly under the sort of rubric of this idea that there is some kind of statistical information that some of the large firms that have access to a lot of our data have might induce us to think slightly differently about various information economics models, but we're going to particularly take up the topic of insurance. So the seed of the question is, with the advent of big data, machine learning, and AI, there is significant increase in data storage and computing powers. Insurance companies can statistically infer things we cannot. So this word statistically is going to be important in the way we model this. And why we call it inverse selection is that instead of adverse selection, could we end up with a situation where there's an inversion of information advantage in classical screening contracts, and if that's true, how should we think differently about modeling insurance contracts or the insurance industry? So one perspective, kind of somewhat historical perspective one could take on this is there these first generation of models which show that asymmetric information matters for markets, especially insurance markets. Markets can unravel, so there is kind of obviously role for market design. Then especially in the context of insurance, we realize that, well, actually we should be thinking of asymmetric information as multidimensional. This could lead to advantageous selection. So it's not just that the high type gets full insurance, it's actually that the high type might also be the less risk averse type or the more risk averse type. And this leads to various kinds of interesting math and also economics about how these contracts should be written down. What we are arguing is that maybe one should also look at, sort of even further and say, actually, the initial endowment of information itself could now be changed. So the way we should look at information is perhaps think about the fact that, and obviously you'll see, there's classical work done on this problem, but not through the informed principle problem and so on, but not in the context of that we're going to present. So I already said this. So let me just set up the roadmap. If you have any questions, please feel free to stop me, or whether they're clarificatory questions or deep questions about the model, please feel free to stop me. So what we're going to do is we're going to set up a model with two-dimensional asymmetric information. Like in the classical Rothschild-Stiglitz and other kinds of models, the agent is going to have some information about some information about her own type, but we're going to make this partial. The agent is not going to be endowed with complete information about her own type. The principal, on the other hand, is going to have some statistical information about this two-dimensional variable, which the agent does not have. So the first difference is going to be that agent has some hard information, the principal has some statistical information. And we're going to look at three cases. One where there is principal has no informational advantage. So this would be kind of the classical Rothschild-Stiglitz setup. In the next two cases, we'll look at situations where principal does have informational advantage. However, we're going to assume that, initially we're going to assume kind of agents are behavioral and don't do Bayesian inference. So a strong force which will sort of be available to the agent, of course, is Bayesian inference. So I offer you some contracts. Could you infer something from it, and how much can you infer? So first, we're going to start with a very simple framework where the agents cannot infer. And then we're going to look at the classical model where agents are rational. And if I have time, I'll have a slide or two on understanding how regulation can help in these sort of situations. Any questions? Okay. So let me set up the model. The model is the following. So we have a risk-neutral principal who's going to offer contracts. One contract, so each contract is a pair where P is a premium and X is the fraction of coverage. So X is a number between 0 and 1, how much of the damage you're going to be insured. And P is the premium, the payment that you have to pay, the payment that you have to make to get this insurance contract. This is kind of standard. And the role of the principal just wants to maximize profits. There is a risk-averse agent who has some initial wealth W, and there'll be some realized loss or damage L. Okay, so L is going to be the damage that could potentially happen to the agent. L is going to be normally distributed. And we make this Kara-Gaussian assumption. You'll see kind of attractability because solving models with risk averse or concave preferences can get complicated. There is going to be some mean mu, which is going to depend on the state of the world. And this state of the world is critically going to be two-dimensional. Okay, so this is why I said in the beginning that we're going to have two-dimensional private information. The mean is a function of this state. So the mean can be either mu high, low, low, high, or low, low. So there are four possible values that the mean loss can take. This mean loss is unknown. So people don't know which state of the world is going to be realized. The theta, which is the state of the world, is going to be jointly distributed according to some joint distribution Q, which is the state of the world. And finally, the agent is has this exponential utility function over final wealth Z. So what does final wealth mean? There's going to be some loss, there's going to be some premium that you pay, and there's going to be some coverage. So taking all of that into account, there's going to be some final wealth Z. Okay, so is this clear? If there are any questions, I'm happy to. So this is kind of the basic structure of the model. There is a two-dimensional state which parameterizes what is the mean loss that the agent is going to go through. And then you have mu L, mu H, mu LH, and mu HH, and so on. Okay. See someone raised their hand.
Yeah, we have a question. I'm gonna.
Yeah, of course. Yeah.
Sorry, Rohit. Just quickly.
Yeah.
So there's two dimension, just LH. So each theta 1, theta I can just be L and
exactly. Yeah. I should have said this. So theta 1 and theta 2 can both take values high and low.
That's it. So, but
right.
This
so
is not literally, I think about two dimension, but that's all right. But it's discrete, right? So, but anyway.
Yeah, it's everything. Everything is discrete. So everything is discrete.
Yeah,
there are four possible realizations. Exactly, but they're not independent. Like, so they have some joint distribution. So this is a random variable and it's distributed according to the joint distribution Q. Okay. So this is the joint distribution. So you can write down it. And this is kind of a two-dimensional 2x2 Bernoulli distribution. There's going to be some marginal Q1 and Q2 over the two dimensions, and the distribution is parameterized by these four variables. Okay. Now, as Taiwei was pointing out, there are going to be only two types in each dimension. What you can do is when you have this kind of distribution, you can rewrite this in the following way. Okay, so the distribution has 3 degrees of freedom, and this is going to be important because here we're going to differentiate between hard and statistical information. So what we're going to say is that the distribution can be completely expressed as a function of the marginals and the correlation coefficient rho. Okay, so this was your starting distribution. I defined Q1 and Q2 to be the marginals here. And what I'm doing is I'm just rewriting this distribution in terms of these parameters Q1, Q2, and rho. Okay, so this is just a standard result. This is nothing original that we are doing here. so each column represents the joint distribution of low, 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 high, high, low, and high. So what possible state is going to be realized. Okay. So this is the distribution is going to be completely parameterized by these three variables. Okay. So what is the key departure that we do from standard models is that we're going to assume that Q1, Q2, and the fact that rho is distributed according to F are publicly known. Okay, so in particular, the marginals are going to be common knowledge. Okay, and the fact that rho is drawn from some distribution F is going to be common knowledge. So this first bullet point is common knowledge amongst everyone. By everyone, I mean the principal and the agent. The second and third bullet point tell you what is private information. So the agent knows the first dimension theta 1. So agent knows exactly the realization of theta 1. So agent knows whether you are in the first row or the second row. Okay. And the principal knows the whole joint distribution. So the principal is going to know rho. Agent does not know rho. Nobody knows theta 2. Nobody knows the exact realization of theta 2. The agent knows the exact value of theta 1, and the principal knows the value of the joint, the correlation coefficient. So what I want you to think about is that we are presenting kind of a partial equilibrium analysis of a much more general model, which is probably one should write down after this. Is that rho is like all of us go to the insurance company with some characteristics. The insurance company constructs rho. Maybe in equilibrium, but we are just assuming that kind of rho is exogenously given, and then once it's able to construct rho, which is kind of the model, or in the spirit of this conference, is some kind of machine learning algorithm that you're using. Now because they've been able to construct rho, they have a very precise information that if you walk in with some information about theta 1, for example, your family history, your genetic pool, where you were born or raised, so putting all this information, they might be able to use their models to predict how likely you are to fall sick and so on. So rho, therefore, we're going to assume that as you walk into the insurance company, the rho is already given to the insurance company, and they can use this to make certain kinds of statistical inference. Okay, in this sense, there's going to be an inverse selection problem. Okay, is this clear? So this is kind of critical. So the model is kind of straightforward. The only thing we want to emphasize was that we want to kind of distribute the information between the agent and the principal in a way that the agent has hard information, the principal has kind of statistical information, and give both of them some advantage, but kind of give a significantly more advantage to the principal than in the classical model. Okay. Okay, so how do we solve this model? So we lay down the model in the following ways. This is the structure. This is also fairly simple. Sort of inspired from Meyerson and other people. We can use what we can say is that we'll have to introduce an abstract object, which is a mediator, and along with the mediator, we'll have to introduce an abstract object, which we will call the message rule. Okay, it's nothing fancy. It's just the fact that if I post a contract, you will be able to infer something from it, and we're going to model that as a message rule. So what is a message rule? A message rule is simply a reporting mechanism that the principal reports. That the principal sees rho, and then it reports some message M. The M can be the complete set of possible correlations, or it can be only 2 messages or 3 messages, and so on. For each message, the principal is going to post a contract. Again, as I already described, a contract is a tuple. It's the premium and the coverage. The contract is going to be a mapping from HL to some real number. Why HL? Because the contract is going to be a function of both the message that the principal is sending and the report of the agent. So I know something about rho. I'm going to decide how finely to use this information rho. And I'm going to observe what, obviously I'm going to give you an incentive compatible contract. So you're going to report theta 1 to me. And then I'm going to offer you a contract as a function of how much of rho I want to reveal to you and what value of theta 1 you've reported. Okay. So how does the game go? The game is that In the first stage, the nature is going to draw some rho and some theta. Sorry, I'm just putting my charger. The seller will learn rho and report it to the mediator. The mediator in turn will generate a message M. The buyer will form a posterior FM because the buyer will see the message. Then a menu is going to be offered, which is a menu of contracts. The buyer will learn theta 1 and report it. And then a contract CM theta 1 is going to be implemented. Okay, and the final contract, as I said, is a function of the message that the principal has sent and the report of the agent. And then obviously the payoffs are realized. Any questions about this? Okay. Why do we use the Kara-Gaussian framework? The Kara-Gaussian framework is very helpful in kind of this is kind of standard finance and asset pricing models. It makes the analysis tractable because it allows us to kind of have all the risk aversion in this term here. We don't have to go into the details, but it makes us life simple. So in the classical model doesn't have this assumption. We had to make this assumption kind of to be able to solve things a little bit more cleanly. But there are various other. I mean, we don't need this. I think we will be able to do the analysis without this, but to get the kind of nice theoretical solutions is necessary. So the objective here is of the dynamic mechanism is to maximize the profit of the principal subject to the incentive constraint of the principal, the incentive constraint of the agent, and the IR constraints for both. Okay. What is the incentive constraint for the principal? Remember, principal is making a report to the mediator. So the principal has to report her type about the correlation coefficient truthfully. So this is the incentive constraint of the principal. Well, we want the agent to also report the type truthfully. So given the message from the mediator, we want the agent to report truthfully theta 1. And under truth telling, we're going to have some profit function and some utility of the agent. There's going to be some message space, which is going to be the support of the message rule R. And then as a function of that, there's going to be a contract space C. And when I do regulatory, we'll have some other regulatory constraints. But for now, this is the description of the problem. We're going to maximize the profit of the principal subject to these three constraints. The principal should report truthfully, agent should report truthfully, and IR constraints. Okay, so let me go on to what would happen if rho is common knowledge. Okay, so suppose that rho is not, it's a Dirac measure. F is just a Dirac measure on rho, and so both parties know exactly what the correlation coefficient is. Then basically we're back in the Rothschild-Stiglitz world, but with a twist. Because no one knows theta 2, everybody's integrating over theta 2 using rho. But the insuree, which is the agent, has more information because the insuree knows theta 1. So this is kind of like the Rothschild-Stiglitz problem. What happens here is, and why there's a twist, is that this is the profit. On the left-hand side, you have the profit function of the firm with respect to the correlation coefficient. There exists some unique value of rho, at which point the agent's private information is not beneficial. Because if I know one dimension, there is some particular value of rho, at which point my information is irrelevant because it's telling me that everything is equally likely. I have no informational advantage. At this point, the principal is going to offer you a pooling contract and extract all the surplus. So that's why and this is going to be important in a lot of the calculations we make, that when rho is common knowledge, the principal's profit function is going to be single peaked. Because there exists some correlation coefficient at which the agent's private information is actually irrelevant. So it's as if nobody knows anything. The principal is just going to maximize ex-ante profits and extract all the surplus. So nobody knows anything extra. And what you see here is that on the left-hand side of this, you're going to give full insurance to the high type, which is in the standard model, and partial insurance to the low type. And on the left-hand side of this peak, you're going to give full insurance to the low type and partial insurance to the high type. By low and high, I mean the dimension of the agent, the information that agent knows. So in the standard Rothschild-Stiglitz model, what you would do is you would give full insurance to the high type and partial insurance to the low type. I'm saying that depending on the correlation, what is high or low becomes endogenous. Okay. The second case we look at is the case where the principal, the rho is not common knowledge. Rho is private information of the principal. So the principal has some statistical advantage. However, the agent is not Bayesian sophisticated. And we model this in a very stark way by saying that the principal is going to post a set of contracts, and the principal is also going to tell the agent what the correlation coefficient is. It's going to tell you, you have a high type and you're very highly likely to get sick, or you have a low type and you're still very highly likely to get sick. And the insuree is going to just simply kind of absorb this information and agree with it. So I go to you not only for a contract, but I also infer something from what you tell me about how likely or unlikely I am to get sick. So we have another version of this behavioral model in the paper, which I'm just presenting the most stark one because it kind of communicates how statistical information plays out in a very stark way. So what would the principal do? The principal is going to do the following. It's going to tell you that the correlation coefficient is the worst if actually you have, is the least possible value if your correlation coefficient is actually quite high. And it's going to tell you that's the highest possible value if it is actually quite low. So it'll try to maximally mislead you. The profit of the principal is going to be uniformly higher. So for any possible value of rho, the principal is going to make a much higher profit than the Rothschild-Stiglitz model, which is obvious because it's kind of misleading you with rho in your incentive constraint. And the contract is kind of going to be generically separating. So what happens is the following. This is your standard graph that I showed you earlier. The profit of the principal is quite high, and it's higher in the extremes because if your types are highly correlated, I will benefit a lot from telling you actually that they're negatively correlated. And if your types are negatively correlated, I'll benefit a lot from telling you that they're highly correlated. And so at the extremes, the profit is the highest. And as I said, you're going to offer, and this is something that doesn't happen in any of the standard models, either in advantageous selection or adverse selection. The principal is actually going to over-insure the agent. Remember, X is a fraction. So when X goes above 1, what you're seeing is that the principal is giving this extreme contract where it's not insuring one type of the agent and it's over-insuring the other type of the agent by a lot. Okay. And then finally, let me present the model where you will have the agent is completely probabilistically sophisticated, so agent can do Bayesian inference, very, very easily. And so here there's going to be the main trade-off. So the standard trade-off in these kind of screening models is rent versus efficiency. So you want to maximize efficiency while minimizing the information rent of the agent. This force still exists because we still have agent private information, but there's a new force which we call belief gap versus price discrimination. So what does that mean? That means that the principal wants to offer a lot of contracts in order to price discriminate the agent and use her private information. But by offering a lot of contracts, the agent is going to infer the private information. And so that's going to reduce the impact of the principal's private information. So the principal will also try to maintain a belief gap. So these two forces determine how many contracts are offered at the optimum. And kind of in this part of the paper, the main result is that actually the principal is going to offer very small number of contracts. So it's going to try to maintain its belief gap from the agent and sacrifice price discrimination.
Rohit, you have 5 minutes.
Yep. So in particular, I don't have time to explain the mechanism, but so these are the parameters, for example, for which this is just a graph where you're going to offer 2 contracts here, and you're going to offer 1 contract here. Why the 1 contract is interesting is because what we're saying is that for a large class of parameters, the principal is going to not use its private information at all. So it's going to offer you a completely pooling contract for all possible values of rho because it understands that if it gives you more than 1 contract, the agent is going to infer kind of which bucket of correlation coefficient does she lie in. So depending on how rho is distributed, the principal actually offers only 1 or 2 contracts at the optimum most of the time. And we interpret this in 2 ways. We interpret this in a way to say that one is that I mean, maybe the Bayesian force is too strong to be realistic in this context, that the fact that the agent can completely infer everything from the contracts is leading the principal to offer only 1 or 2 contracts. The other way to interpret this is to say, well, if the agent is not being able to interpret what contracts is being offered to her, then it is precisely then that the principal can make a large amount of profit from using sophisticated techniques like machine learning and AI. So there should be a large market kind of, at least in our model, for data brokers, for people who understand and can educate, or kind of data activists almost, like who can educate the agent about how their data should be interpreted, given what they're observing about the contracts they're getting. Okay, so basically, in the end, in the last part of the paper, what we say is that, how about in this market, if the government steps in and forces the principal to reveal rho? The government says, no, this cannot be private information. You have to reveal rho. And we kind of model this in a specific way by saying that now the insurer has to be incentivized to reveal the information rho. And this leads to kind of a lot of other interesting situations about welfare and is it welfare improving? Is it better for the whole kind of health industry to force the principal to reveal this information? And what we find is that, well, it's better for the consumer, but it's worse for total surplus. So total surplus goes down quite a bit, but the consumer's utility goes up. Okay. So kind of just to wrap up, what we want kind of you to take away is that we should perhaps think more systematically about asymmetric information models, which assume most of the endowment of asymmetric information is on the side of the agent, given how large firms are now able to process our own information statistically and make inference and arguably monetize it for profits. What we basically showed was that we modeled this as the principal having statistical information and the agent having some hard information. In the rational model, the insurer trades off this belief gap versus price discrimination in front of the former. And one can ask oneself, well, do we see very little price discrimination in the market where big data is involved? If yes, then maybe this is one way to rationalize this. However, if the insurer is not Bayesian, is quite gullible, then this leads to large profits for the principal. This should introduce a role for people in the market who can kind of advise consumers about how to use data for their own benefit. In the last part of the paper, which I didn't have time to talk about, we talk about regulatory interventions where the government can force the principal to reveal this private information. And one interesting aspect, which we haven't seen in many other theoretical papers at least, is that you will see overinsurance being used by the principal, especially when the agent is naive or gullible. Well, I can stop here now.